Well, I hope that by now you're feeling pretty confident about taking these exponential functions and transforming them into logarithmic functions. Uh, one of the one of the things that we need to be able to do to complete the circle here is to take these logarithmic functions and go in the reverse route. In other words, take this linear relationship and transform it back into this exponential relationship. So the way we do that, if we look at these, if we look at the terms in this equation, the log of the natural log of phi, the natural log of phi is basically it's the power that you have to raise, and we've said this over and over again. It's probably it's sounding familiar. It's the power that you have to raise the base e to in order to get phi. So if this basically implies that e to the log of phi is going to give us phi. Now, some of the difficulty comes in when we take what you remember, in order to maintain equivalence in the operations, the mathematical operations we perform on an equation, we need to be sure to do what we do to one side of the equation we have to do to the other. So just to maintain equivalence here, we need to raise this side. We need to use this side of the equation as the power for the base e, and that would give us a log of phi 0 minus lambda t. Now it might be tempting to think of this as e to the log of phi minus e to the lambda t, but remember your basic rules. If we have something like e to the a plus b or e to the a minus b, that what this gives us, using these powers and the rules we use for manipulating powers, we know that this is equal to a to the b, or a to the e to the a times e to the b, and this would be equal to e to the a times e to the minus b. So over here in this term, we should think of this as e to the natural log of phi 0 times e to the minus lambda t. And you can see already that we've got this term. So let's write what we have. We have, from this left side of the equation, we have phi. Let's write down phi. This is equal to e to the natural log of phi 0, the porosity at a depth equals 0, times e to the minus lambda t. And think about this term again. How should we be thinking about this exponent here? This is a constant. It's the power, this log of phi 0 is the power that we have to raise the base e to in order to get phi 0. So e to the natural log of phi 0 is just phi 0. So we have phi 0 e to the minus lambda t, and we've gone pretty much full circle back up to this exponential relationship. So I hope you're beginning to feel comfortable with that. I think we've also spent some time talking about this Gutenberg-Richter relationship. And this is just another logarithmic expression. It has a log on one side, and it has the earthquake magnitude and another constant on this, a couple constants on this side. This constant is the slope. This is the independent variable. and this is just the intercept. Let me just draw a quick plot over here. And we've got our independent variable is m. We've got our dependent variable, which is the log of n. N is the number of earthquakes of magnitude m and higher. So the slope is negative, so we have a line that looks something like this. So for any individual value, come over to this line, we have a particular log of n, let's say n sub I, for a magnitude m sub I. This log of n sub I, n sub I is the number of earthquakes of magnitude m and larger. So it includes not only earthquakes of magnitude m, but earthquakes of magnitude m and larger. And there's usually a time associated with this, and that time frame would usually be per year. So be the number of earthquakes of magnitude m and larger per year. So the question is, if we solve this, if we derive this expression, if we figure out what the slope is and what the intercept is, we solve for the log of n, how can we figure out what n is? Well, we know that the log of n is just the power that we raise the base to. In this case, the base is not e, the base is 10. So it's the power that we raise the base n to in order to get n. So if we solve this equation for the log of n, then all we need to do is raise 10 to the log of n power in order to figure out what n is. And this is usually a number of events for some time interval. Okay, well, we have this side of the equation. We've transformed that into n. And, as we've said all along, if we want to maintain equivalence in our mathematical manipulations, we have to, what we do to one side of the equation, with one side of the equation, we have to do with the other. So what we need to do now is raise 10 to the power minus bm plus a. So that's a minus bm plus a. And by now I think you know what we need to do with that. That's going to give us, it's going to be equal to 10 to the minus bm times 10 to the a. And we could just refer, this is just a as a constant. 10 to the a would be a constant. We could let that equal to k, let's say. And then we could write this, our result then is going to be, it's going to look like this, where we have the number of events of magnitude m and larger is equal to 10 to the minus bm, but we have this constant k in here. So we have k times 10 to the minus bm. And again, if you have questions about this, come around. Hopefully this is beginning to look familiar to you and you're getting comfortable with these transformations.